All right, so let's continue here. We're going to start in on our next chapter, chapter 5, which is on stereochemistry. And we kind of covered this a little bit last week as well when we introduced the idea of cis and trans stereochemistry. All right, remember that this arises because those cyclic structure, those rings, cannot fully rotate. So if we have, for example, a cyclohexane ring, and we put on there two methyl groups that are pointed in the same direction, then they're going to be locked on those same side of that ring, because that ring can't fully rotate. Those carbons can't fully rotate. And this would be a distinct molecule then if one of those methyl groups was pointed up out of the page and the other was pointed down into the page. These would be two distinct molecules, right? You can't any way sort of rotate this in order to become that other one. That's why we have our two stereochemical distinctions here. When they're on the same side, which isomer do we call that? The cis or the trans stereoisomer? So same side would be the cis, opposite side would be the trans. All right? Cool. All right, so we're going to sort of pick up where we left off last week. We spent a lot of time not only talking about this stereochemistry, but then specifically talking about these cyclohexane rings and the fact that they do not form these regular hexagons like we draw on paper here, but instead they adopt what we call our chair conformation, which allows all those carbons to have those ideal bond angles and allows all those bonds to be staggered, so nice and stable structure for those six-membered rings. All right, we're going to grab one of our bond line structures here because that's kind of the last step that we have to do with our chair structures. All right, so let's take out our last of our chair templates that we have. I also have some extra printed out if anybody would like to grab one, or to have just an extra to study with, whatever you want to do. Okay. All right, but we're going to take this chair structure here. Remember last time we looked at a molecule where I started you out with this chair structure here where we had these two methyl groups on there. And then we mapped what would happen as our chair flip occurred. Remember that when we have our chair flip, all of our axial positions become equatorial positions, and vice versa, all of our equatorial positions become axial positions. But for that problem, I started you out in a chair structure. The last thing that we're going to do is we're going to be starting out in a bond line structure, and we have to figure out how to map this thing here into our chair conformation. All right, that's the name of the game here. Okay, cool. So first of all, since these bonds are both on these wedges here, does that mean that the bond is pointed out at me or into the page? Out at me, right? So I'm going to say that these are both pointed up here. So when we map to our chair structure over here, we're also going to make sure that they're both pointed in that on that up bond. All right, so I'm going to number my carbons in my chair structure as well. I always like to make this carbon that is the furthest to the left here, carbon 1. I think that that's the most convenient. If we look here, this carbon sitting furthest to the left on our drawing. I like to make that carbon 1. Okay, so then just going around our ring here, carbons 2, 3, 4, 5, and 6. And we're going to number our carbons in our bond line structure as well. Carbon 1, 2, 3, 4, 5, 6. So this is just to help it make it easier to see what I'm trying to map here, I need to be putting a methyl group on that upward facing bond on carbon 1 and a methyl group on that upward facing bond on carbon 3. All right, everything else is just hydrogens. So if I look at my chair structure here, one of these bonds is on top. This is my up bond. One of these bonds are on the bottom. This is my down bond. And which one am I going to put my methyl group on? The one that's facing up, because again, we said it was on a wedge, so it's pointing out at us. So now let's do the same thing on carbon 3. Everybody take a second. Put the methyl group where it should go on carbon 3. All right, again, I have my two bonds of carbon 3, one pointed up. Whoops. The other one pointed down. I want to put that methyl group on that up bond. All right, so now I want everybody to take a second and figure out whether these methyl groups in our chair conformation are sitting in the axial position or the equatorial position. All right, on carbon 1, which one is it, axial or equatorial? So it's the equatorial position. And what about on carbon 3? That's also in the equatorial position. Remember, your axial positions are pointed straight up on every other bond or straight down on every other bond. Your equatorial positions are the ones pointing away from the ring. So I'm going to say for this one here, they are both in that equatorial position. All right, so I built my model kit here, my cyclohexane ring, and I have these two methyl groups that are in, actually I guess their axial positions were pointed down, right? So I guess I should put it like this. Both of them are in those equatorial positions. Our two methyl groups are in those equatorial positions, right? Pointed away from the ring. One here, one here. Okay, so now I'm going to do my chair flip. Remember, by chair flip, I don't mean I'm going to flip over the molecule because I haven't actually changed the structure at all then. Our chair flip is a rotation about these carbon-carbon bonds. They can't fully rotate, but they can kind of wiggle themselves around. And what we're going to see is, again, our axial positions become equatorial positions, and our equatorial positions become axial positions. All right, so here's my chair flip structure. Now these two methyl groups I can see from the side here are sitting not in the equatorial position, but in the axial position. All right, so let's go back to our template here. And we got to draw our other chair conformation. And since we know that they're both in the equatorial position over here, what are they both going to be in over here? They're both going to be in the axial position. All right, but let's make sure that we can sort of follow everything correctly. Again, like I said, the furthest carbon on the left, we made carbon 1 on this structure. We're going to do the same thing over here. The carbon that's the furthest to the left is going to be carbon 1. And then we're just going to go in that same clockwise direction. All right, importantly, in order for me to have done my chair flip correctly, my carbon that was located, my carbon 1, it's located at a valley on my one chair structure. That means it needs to be located at a peak in my other chair structure. That's how we make sure that our chair has flipped correctly. All right, so I've mapped that carbon correctly over here. And now I'm going to look. Again, I have these two bonds, one up, one down. I didn't break any bonds, so my methyl group is going to be on that carbon 1, on that up bond. It's just now that up bond is in the axial position. All right, so then do the same thing. Take a second and map it to the correct position on carbon 3. right, again, I have one bond pointing up, one bond pointing down. I need to put it on that bond pointing up. It's just now that up bond is in the axial position. Okay, so then the last thing that I could ask you here is which one of these two chair structures, which one of these two rotational states is more stable? Right, so this molecule is going to flip back and forth between these two conformations, but it might prefer one over the other depending on the stability of those two rotational states. All right, so going back to my model kit here, remember those methyl groups are kind of big and bulky, right? So if they're in the axial position here, they are right next to each other. Do atoms like being right next to each other? No. So what we want to just convince ourselves real quick is that in this axial position, these methyl groups, they don't have very much room. They're in this very crowded environment. If we flip it back to our other chair conformation, to where these two methyl groups are in the equatorial position, they have much more room between neighboring atoms, right? So these methyl groups, these big bulky groups, they want as much room as they can have. There's more room available to them in the equatorial positions than in the axial positions. So if I'm going to ask you which one is more stable, we're going to choose the conformation where they're both in that equatorial position. This one's more stable, meaning our molecule will spend more time in this rotational state than this rotational state. All right, and again, how do we address the question of which one's more stable? Those large groups like to have more room, meaning they prefer the equatorial positions. All right, so this was kind of the last step in our discussion of these cyclohexane chair conformations. Again, cyclohexane adopts this chair conformation because it allows it to have these ideal 109.5 bond angles as well as these staggered bonds. All right, so it's just more stable in this chair conformation. The last step was taking our bond line structures, how we draw our molecules in 2 dimensions, and mapping them onto this chair template here. All right. And then we got to monitor these groups as we do our chair flip. So making sure we can map from one side to the other here. And then lastly, addressing which one of those two conformations would be the most stable. Again, if we have any large groups on there, those large groups are going to prefer to be in the equatorial position. Cool. All right, so now we're going to move on to our new type of stereochemistry. So with rings, we had the cis-trans stereochemistry. All right, now we're going to talk about chiral stereochemistry. All right, and this is something that arises because of an sp3 hybridized carbon's tetrahedral geometry. All right, now not all carbons are considered to be chiral carbons, so that's kind of our step one, is to identify our chiral carbons. All right, so chiral carbons, otherwise referred to as chiral stereocenters. All right, so like we said, this is a consequence. So in order to be a chiral carbon, you're an sp3 hybridized carbon, meaning you have that tetrahedral geometry. All right, so we're going to take a look at a tetrahedral geometry here. Actually, before we draw it, let's get one in front of us. So everybody's going to grab one of the model kits in front of them and take out one of the black beads, which is a carbon atom. Make sure your carbon atom has 4 holes on there. There are some very close to black, but really dark blue ones that have 5. And then you're going to take 4 of the little stubby bonds to create your tetrahedral. All right, so a black marble and 4 little stubby bonds to create a tetrahedral geometry. We're all going to make a tetrahedral here. Let's hold up our tetrahedrals. Beautiful. Okay, so let's first draw a bond line structure that accurately represents our tetrahedral geometry. What we're going to do is we're going to hold it such that 2 bonds are in the plane of the page, which means 1 bond sticking out at you and the other one's pointed into the page. So everybody orient your tetrahedral so that it looks where 2 bonds are in the plane of the page. We have 1 bond pointed out at us. And then we have 1 bond pointed into the page. So here's our tetrahedral geometry here. All right, but in order to be a chiral carbon, not only do you have to have that tetrahedral geometry, be an sp3 hybridized carbon, but you have to have with 4 distinct bonds. Or let's say, actually I lied, we're going to say bonded to 4 distinct groups. All right, so what we're going to do is we're now going to pull 4 distinct atoms out from our bin here. We're going to pull a red one, which is oxygen, a blue one, which is nitrogen, a white one, which is hydrogen, and a black one, which is carbon. So everybody take 4 different colored beads, white, black, red, and blue, and add them to your tetrahedral. All right, so now what we've done is we've all created a chiral carbon, right? A carbon that has that sp3 hybridization. It's got that tetrahedral geometry, but it's bonded to 4 distinct groups, 4 distinct atoms here. Okay, and what I want you to do is to compare your molecule to your neighbor. See if you have an identical molecule. All right, you'll know they're identical if you can what we call superimpose them. So if I were to drag this over, would it perfectly line up with my neighbor's molecule? Or is it not superimposable? Do you have, in fact, 2 distinct molecules? All right, so compare them with your neighbor and see whether or not you have the same molecule or 2 distinct molecules. those the same? No, those ones you can't superimpose. What about y'all? Oh, so you don't have the tetrahedral. Be careful. You got to grab a different marble that has, you have 5 holes on that one. You're going to need one with only 4 holes. All right, are these the same thing? Those ones we can superimpose. What about these ones? Are these the same thing? Can we superimpose these ones? No, they're not going to line up perfectly. In fact, they are mirror images of one another instead. What about y'all? You have the same thing or different? You have the same. What about you, Zach? I think you got the wrong geometry as well. Oh, no, you're good. Did you guys? So let's compare these two. Are these? Oh, whoops. Oh, these are the same too. Okay. Cool. All right. So we could have drawn identical molecules that we can superimpose. So for example, this pair up here, these are the same 2 molecules, right? I can superimpose. Or I could have had 2 distinct molecules that I cannot superimpose onto one another, all right? These is the exact same arrangement, the exact same carbon, same chiral carbon in the middle. It's got the same bonds, but I do not have an, oh, whoops, these ones are the same. Oh, hold on. Cool. All right, these ones are 2 distinct molecules here. I have the same hydrogen, carbon, oxygen, and nitrogen, but I cannot superimpose these. These are not the same molecule. In fact, they are mirror images of one another. All right, and that is our chiral carbon. These are 2 distinct molecules. All right, we're going to have, similar to how we had cis and trans, we'll have R and S stereochemistry for these, but these are 2 distinct molecules. They have the same chemical formula. They have the same types of bonds, but there's a different spatial arrangement of these atoms. Okay, so this is what we would call a pair of enantiomers, these mirror images of one another. So here's my first molecule, and now I'm going to draw its mirror image. All right, so these are 2 distinct molecules that are mirror images of one another. All right, and again, this is what we would use this term. These are enantiomers. Enantiomers, these are stereoisomers that are mirror images of one another. All right, so I have my chiral carbon, my carbon that is bonded to these 4 distinct groups. And when we have these chiral carbons, then these mirror image molecules are not identical. They are not superimposable. They are themselves distinct molecules. And that pair of mirror image molecules, we call that a pair of enantiomers. Our stereoisomers, our chiral stereoisomers, They tend to behave very, very similar. These would have essentially identical melting points and boiling points. Their physical properties would be very similar. If you get like a really big complex molecule with multiple chiral centers, that might not always be the case. But generally speaking, chemically, these things behave very, very similarly, but they are not identical molecules. They are themselves distinct molecules. All right, so step one, we should be able to identify chiral carbons, carbons in our molecule that are bonded to 4 distinct groups. And now we're going to work on drawing enantiomers, drawing their mirror images. All right, so let's take an example. Okay. So first, we want to look at this molecule and figure out whether we have any chiral stereocenters. Are there any carbons in this molecule that are bonded to 4 distinct groups? There are. Where is it? All right, so how is this carbon here chiral? How is it bonded to 4 distinct groups? Well, it's bonded to a methyl group, an ethyl group, a propyl group, and what's that 4th bond? Hydrogen, right? So those are indeed 4 distinct groups that are bonded to that carbon there. So we can draw the enantiomer of this molecule. And we're going to have a few different methods of drawing enantiomers. Really, we want to be able to spy when we're looking at an enantiomer of our compound. The first one is what we're going to call simply that mirror image method. Remember, an enantiomer is a mirror image, so we can pretend like we have a mirror here, and we're going to draw that molecule's reflection in that mirror. All right, so let's imagine that we have a mirror here. This molecule is looking at itself in the mirror. What's this molecule going to see? All right, so now I'm going to have to start my next bond going down, right? If it's looking in the mirror, it's going to be its reflection. I'm going to color code these carbons just so we can keep track of them a little bit easier. All right, if this thing's looking in the mirror, what color carbon is it going to see first? That red one, then the orange one. Now I'll have my other carbon, and this one has that wedged methyl group. Then we have our green carbon, our dark blue, and our light blue. All right, so we can draw the enantiomer of our molecule of interest by drawing a mirror image reflection of that molecule. All right, that would be one way that we could draw an enantiomer. All right, let's do another way. We're going to call this our dash to wedge method. All right, so if we take our molecule, we'll take that same example. Okay. If I wanted to draw the enantiomer of this molecule, what I could do is I could take that wedged bond right there and just flip it so that it's a dashed bond. Or vice versa, if I have a dashed bond on there, I would flip it to a wedged bond. All right, so here I could get my same molecule, or rather I could get my molecule's enantiomer by changing that wedge to a dash. These are now also a pair of enantiomers. All right, let's take a second to convince ourselves that this works by looking at a model kit. All right, I put a green marble on there so we could see these bonds a little bit easier. And first thing we want to do is convince ourselves that we are indeed looking at a mirror image pair of molecules here, right? They're mirror images. So what we did when we drew our first method of drawing enantiomers was to draw that mirror image, imagine a mirror here, and draw its reflection. What we could also do is just flip that dashed bond to a wedged bond. So notice in one of my pairs, that green marble is pointed out of the page, would be on a wedge. In my other, in its mirror image, I simply have that green molecule now, or that green atom pointing into the page, right? So that would be another method of drawing our pair of enantiomers. I could draw them as mirror images, or I could just flip the direction of those wedged bonds to be dashed bonds, or dash bonds to be wedged bonds, right? So both of these are methods of drawing. To be clear, these are the same molecules, right? That means that these are also the same molecules, just drawn from a different perspective. If I were to take this molecule and scoop it up with a spatula and flip it over like a pancake, I would be getting this molecule here. So same thing, just drawn from a different perspective. All right. And the last one is what we're going to call our swap group method. All right, I guess to be clear, our dashed wedged method, this was to change dash to wedged. And wedge to dash. All right, our swap group method helps when we have a tetrahedral type structure. The other two are more helpful for bond line structures. If we're actually looking at that tetrahedral stereocenter there and we want to draw the enantiomer of this molecule, we could use that mirror image method. That's what we did before. But let's also kind of just note here all right, again, I have my mirror image pair of molecules. We can see that these are mirror images of one another. What if I took that carbon and that hydrogen and I kept it in the same orientation? So my carbon's on the left here, my hydrogen is up top. What do we notice about those blue and those red marbles between those two enantiomers? I've traded positions, right? So I can also draw an enantiomer by swapping two of those groups about my tetrahedral carbon. All right, so for our swap group method, we're going to keep two groups the same. And then swap the other two groups. All right, so if I'm going to draw the enantiomer of this molecule here, I'm going to keep that carbon and that hydrogen in that same exact position, and I'm just going to trade my red and my blue marbles from one another. This is also a pair of enantiomers. All right, I swapped these two here in order to draw my pair of enantiomers. All right, so all three of these methods here are methods that we could use to draw enantiomers, to draw these mirror image pairs of molecules. You're going to be asked to do all three of them, and more importantly, we want to be able to recognize when we're looking at a molecule that's the same molecule or a molecule that is an enantiomer. So we want to get good at practicing drawing these mirror image pairs here. So we could either use our mirror image method, we could use our dash to wedge method, or our swap group method. Either one of these is a way to draw a pair of enantiomers. All right. Cool. So with rings, we had these cis and trans stereochemistry. For chiral molecules, we're going to have something kind of similar, and that's what we're going to discuss now, is how to assign what's called R or S stereochemistry. All right, so let's grab one of these examples here. Okay, so remember, our white marble represents hydrogen, our black marble represents carbon, our red marble represents oxygen, and our blue marble represents nitrogen. Okay, so step one, we have these four distinct groups about our chiral carbon, right? That was a necessity in order for a molecule to have an enantiomer, to be chiral. It has to have that stereocenter. All right, so to each of those four groups, we're going to assign what we call priority to those four distinct groups. All right, so what exactly do we mean by priority? Okay, priority we're going to assign based on atomic number. The higher the atomic number, the higher the priority. All right, so if we go to a periodic table here, we have hydrogen. I don't know why this is frozen. I don't know, it glitched out right here. Anyways, hydrogen's atomic number is 1, carbon 6, nitrogen 7, oxygen 8. So what's my highest priority group? The oxygen, and then the nitrogen, then the carbon, then the hydrogen, right? So based on atomic number, so this thing's frozen, let me reset. All right, but based on our atomic number, we're going to assign priority to those four groups. Cool. All right. So oxygen's highest atomic number, that gets priority 1, then nitrogen, then carbon. Last is going to be that lowest atomic number, hydrogen. So I've assigned these groups priority. All right, I'm going to leave a little bit of space here because we're going to talk about more complicated ways of assigning priority. But for this simple example, we can move on to step 2, which is we need to rotate our molecule. All right, we need that lowest priority group pointing into the page. Which means I want it on what? A dash, a wedge, or a straight line bond? I want it on the dashed bond here, all right? So what I'm going to do is I'm going to take this molecule and we're going to rotate it. So how are we going to do that? Let's take a look at our model kit here. All right, so this is my tetrahedral that I've drawn with my carbon pointing up, my hydrogen pointing off to the left. I have my nitrogen pointing out of the page and my oxygen pointing into the page, but I want that lowest priority group to be the one pointing into the page. So I'm going to rotate my molecule here. I haven't changed my molecule. I didn't break any bonds. All I'm doing is changing my perspective of this molecule, right? And so what I'm going to do is I'm going to rotate. What am I going to do to those bonds? Let's look carefully at what happens to the position. We're going to note that oxygen is going to go to nitrogen's position. Nitrogen is going to go to hydrogen's position. And hydrogen is going to go to oxygen's position. So when I rotate this here, now my hydrogen is pointed into the page, my oxygen is pointed out, and my nitrogen is pointed off to the left. So how do we rotate looking at our tetrahedral structures on our page? We're going to rotate these groups around. All right, so now let's just move these off to the side. I got to put my nitrogen, my hydrogen, and my oxygen on there. Where's my oxygen going to go? Dash, wedge, or straight line? It's going to go on the wedge. What about my hydrogen? Dash, wedge, straight line. The dash, my nitrogen over here, right? So I've rotated these bottom groups. My hydrogen went into this position, my nitrogen this position, my oxygen that position, my nitrogen that position. So now we've rotated our molecule such that that lowest priority group is pointed into the page. All right, and then the last step here is going to be to apply our RS rules. All right, what we're going to do is draw arrows to connect 1 to 2, 2 to 3, and 3 back to 1. All right, so looking here, I'm going to draw in these arrows that connect my first priority group to my second priority group. Oxygen to nitrogen, 2 to 3, and then 3 back to 1. Okay, and I'm going to look, did I draw my arrows in a clockwise direction or a counterclockwise direction? In this case, which way are we going, clockwise or counterclockwise? So that's clockwise. All right, so connect 1 to 2, 2 to 3, 3 to 1, not back to 3, that doesn't make any sense. 3 to 1. Okay, if if our arrows were clockwise, that's what we call the R stereoisomer. And if instead we connected these things in a counterclockwise way, that would be my S stereoisomer. So in this case here, because I connected these in the clockwise manner, we would conclude that this is an R stereoisomer. Okay. Let's take our molecule and let's use that mirror image method to draw its enantiomer. Be lazy and go quick. All right, so let's look at RS and enantiomers. All right, as we said, this one on the left-hand side, this was our R stereoisomer. So now let's assign stereochemistry to its enantiomer over here. We have that lowest priority group pointed in the back. So now we just have to draw our arrows from 1 to 2, 2 to 3, and 3 back to 1. And now I'm going in the counterclockwise direction. I'm sorry, now I'm in the counterclockwise direction. So this would be which stereoisomer? The S. All right. All right, so the R and the S stereoisomer, this is our pair of enantiomers. When I draw my mirror image of my molecule, I'm flipping its stereochemistry from R to S or S to R. Okay. For this particular chapter, these model kits are really, really helpful. Okay. You can see I've been using them to sort of demonstrate this mirror image business quite a bit. It's just nice to have these things to take to spin around because we can do that on the page, but it's a little bit more confusing than if we just take it and spin it around in our hands. All right. We're going to do a practice problem real quick. We're going to stick with this single chiral carbon here. All right. In our kits, we have these orange, green, and purple marbles. So everybody grab one of each of those. These are used to represent our halogens. All right, and I want you to build the following molecule and then assign it as having either R or S stereochemistry. Purple is used for iodine, orange is used for bromine, and green is used for chlorine. So we're going to take this molecule here and we're going to assign R or S stereochemistry. Oh yeah, sorry, iodine has the highest atomic number, then bromine, then chlorine. All right, so here is my molecule as I had drawn it, with my hydrogen pointing out of the page, my iodine pointing into the page, my bromine is straight up, and my chlorine is off to the left. But now I need to rotate this such that that hydrogen is pointed into the page. I'm going to rotate the other direction this time. All right, but again, you can notice that those three groups on the bottom just switched positions, right? So in order to rotate this, I'm going to bring my hydrogen over to my iodine to where my chlorine was, and my chlorine to where my hydrogen was. Oops. All right, so again, I took this and I rotated it. All right, and I had sort of mentioned this out loud, but let's put it in here. Assigning priority, my iodine is priority 1, followed by my bromine, followed by my chlorine, and then that lowest priority group, the hydrogen, is pointed back. And now I'm going to connect 1 to 2, 2 to 3, and 3 back to 1. And so this would be what? The R or the S stereoisomer. In this case, I'm going in this clockwise direction. So this is our R stereoisomer. All right. So now let's take this molecule. All right, our same alkyl halide that we had started out with. And what I'm going to do is I'm going to swap 2 of these groups here. Doesn't matter which one you choose. I'm going to keep 2 of them the same and swap the other 2. If I was going for the speed record here, what would be my stereoisomer assignment, R or S? So it is S. How do I know that it's S? So I could do that. I could definitely just do it the long way where I then put that hydrogen in the back and I could convince myself that way. But remember, when we swap two groups, that's one of our ways of drawing an enantiomer. So since I swapped these two groups here, I know this is the enantiomer of my starting molecule, which means that I also must have flipped my stereochemistry from R to S, okay? So if we can get good at recognizing when we have these mirror image pairs, we can shortcut things a little bit. All right, so yes, this is the S stereoisomer. Because I used that swap group method. To draw my enantiomer. But yes, if you're ever sort of stuck, you can always do it the long way as well, where I rotate my hydrogen to the back, and then I draw my arrows from 1 to 2, 2 to 3, and 3 back to 1, and you would arrive at that same conclusion. Okay, so that's all well and good when we have these tetrahedral structures that we're looking at, but we're actually more used to looking at molecules in what we call our bond line structure, not in these tetrahedral kind of structures here. All right, so how do we assign R and S? For bond line structures? Real quick, does this molecule right here have any chiral centers? These are both methyl groups here, so I do not have 4 distinct bonds. Just because you see a dash and a wedge doesn't automatically mean that you have a chiral center. These are both methyl groups, so at least as I've drawn it here, this molecule doesn't even have any chiral centers. All right? However, I'm not going to stop there. I'm going to instead make this wedged bond a hydroxyl group. And now we do have that stereocenter. All right, but again, step 1 was being able to spy those chiral carbons. They have to have 4 distinct groups bonded to a carbon in order for it to be chiral. Okay, so this is sort of best case scenario here. If I see a molecule like this one's really easy to assign R or S stereochemistry to because I have that hydroxyl group pointed out at me, which means that what's that other bond that's pointed into the page? A hydrogen, right? So that means that there's a hydrogen on that dashed bond, which means that it's pointed into the page, which is our normal way of assigning R and S stereochemistry. All right, so this first case here is where we have our hydrogen on a dashed bond. All right, this is best case scenario because we're just going to use our normal R and S rules, where clockwise was R and counterclockwise was S. All right, hydrogen being that smallest atomic number is our lowest priority group. It's already pointed into the page. What's our highest priority group in this molecule, or rather about this chiral carbon? The oxygen, that's got the higher atomic number. All right, but now we get one of our special cases of assigning priority, where if I look at my other 2 groups, they're tied. I got a carbon over here and a carbon over here. right? So neither one of those atoms bonded to that chiral carbon has a higher atomic number. So how do we break our tie here? So like we said, we left some room up on our assigned priority. Okay, if we have a tie, we're going to list all the bonded atoms. To those tied atoms. Okay, we're going to just make a note here that if it's a double bond, list atom twice, or if it's a triple bond, list it 3 times. All right, we'll show some examples of that later on here. All right, so how am I going to do this? Let's just note here, I use these different colors. So this carbon I colored in blue here, this carbon I colored in red. They both are bonded to that purple chiral carbon, so we don't even bother to include that one on our list. We're going to list its other 3 bonds. So this red carbon over here is a methyl group. So what are its other 3 bonds? They're all hydrogens. So I'm going to make this list. Hydrogen, hydrogen, hydrogen. My blue carbon, what are its other 3 bonds? 2 hydrogens and a carbon, yeah. So I have for my list for my blue carbon, it's a carbon, a hydrogen, and a hydrogen. And I can see that in this list here, now I'm going to look at the atomic number of my listed elements here. Whichever one's higher wins, right? So the fact that this blue carbon is bonded to another carbon, whereas my red carbon is only bonded to hydrogens, that's how I'm going to break this tie, and my blue carbon is going to win. So this is 2, and that methyl group is 3. All right, so when we're assigning priority, we go based on atomic number. If we have a tie in our atomic numbers, we list all the atoms that are bonded to that atom, and we look at the atomic numbers on that list. So here I'm comparing my carbon to my hydrogen. So that's why that blue carbon gets priority 2. And now it's the last step that we do. Connect 1 to 2, 2 to 3, 3 back to 1. So this would be our S stereoisomer here, right? I went in the counterclockwise direction. All right, so now let's take a very similar molecule. Okay, but I'm going to, instead of putting that hydroxyl group on a wedged bond, I'm going to flip it to a dashed bond. So speed record, which stereoisomer am I looking at here? The R. How did we know it was the R? Because I used one of my methods for drawing an enantiomer pair, right? All I did was swap my wedged bond for a dashed bond. So these two have to be a pair of enantiomers, which means if this one's S, this one down here has to be R. Okay, great. But then how would I do it? If I just walked up on this molecule fresh, if I didn't know what its pair already was. And this is a bad case scenario here, because unlike before when my hydrogen was on a dashed bond, so it was already in the correct orientation pointing into the page, right? That was the nice thing of it being on a dashed bond. It was already into the page. Now, what's my hydrogen on that chiral carbon going to be on? Now it's on a wedged bond. So this is our second case here. We have our hydrogen on a wedged bond, which means that it's pointed out of the page. All right, so there's sort of two ways that we could go about doing this here. The first is to redraw our molecule so that the hydrogen is pointed in the direction that I want it to be, which is pointed into the page. All right, so method one is to redraw. All right, and again, model kits can be super helpful here. So let's look at our model kit for this. I have my oxygen pointing into the page here, which means that my hydrogen is sticking out at me. If I want to take this same molecule and redraw it such that the hydrogen is pointed into the page, I got to scoop it up like a pancake and flip it over. All right, so I could redraw my molecule like this, where now my hydrogen is pointed into the page and my oxygen is pointed out of the page. Okay, so if I flipped this thing over, I would get something like this. All right, and then we could take this and we would simply apply our normal rules. All right, but I don't really like this method here because there is a lot of error in taking this molecule and flipping it over and redrawing it in this conformation here. It can totally be done, and when you get really good at seeing these molecules in 3 dimensions, you can do it without error. However, it's a really easy place to kind of stumble and accidentally redraw your molecule incorrectly, and then you get led to the wrong answer, right? So since this redraw thing right here is kind of tough, I prefer method 2, which is to keep my molecule exactly as it is here, but now we're going to flip our RS rules. So instead of using my normal rules, I'm now going to flip my RS rules such that now clockwise is S, and counterclockwise is R. So we can either flip the molecule itself and then apply our normal RS rules, or we can keep the molecule as it is and instead flip our RS rules. And again, I just think that this method is a lot less error prone. It tends to be a lot easier for students. Either one of these would work, though. Importantly, either one of them would take you to the correct answer. All right? So now when I go through and assign my priority, again, that oxygen's priority 1, that ethyl carbon is priority 2, and that methyl carbon is priority 3, I'm going to connect these in that counterclockwise direction. But since my hydrogen is pointed in the wrong direction, it's pointed out of the page, I'm going to flip my RS rules. So now counterclockwise is that R stereoisomer. All right. So for our bond line structures, there are 2 possibilities here. One, that lowest priority group is already pointed into the page. Kind of best case scenario, we just use our normal clockwise and counterclockwise rules for RS, right? Assign priority, clockwise is R, counterclockwise is S. Or if we have our hydrogen pointing out of the page, that lowest priority group pointed out of the page, we either have to flip our molecule around so that it's pointed into the page, or we can flip our rules around and just leave the molecule as it is. All right, so that's how we're going to assign our RS stereochemistry for these bond line structures. All right, so we're going to finish up here. You're just going to do these two examples for me. So then they're tied on their list, right? So then you just move on down the line. So since these two have the same list, you're going to move on to the next atom and do their list.
So then this would be one.
Yeah. Yeah. All right, so let's do this first one here. Chlorine has that highest atomic number, so that's priority 1. I look here, and these are both carbons, so they're tied. So I'm going to make that list of the atoms that they're bound to. And I can see we got a break in our tie. So this is going to be priority 2, and this is priority 3. I'm going to connect 1 to 2, 2 to 3, and 3 back to 1. And since I went in the clockwise direction, this one is which? The R stereoisomer. And I guess I should have noted I'm going to apply my normal rules because my hydrogen, my lowest priority group, is pointed into the page. All right, we're going to go over here. We need to assign priority. Okay, now we're got a 3-way tie, carbon, carbon, and carbon. So I'm going to make my list here. The blue carbon is bound to a carbon and 2 hydrogens. The red one, a carbon and 2 hydrogens. And the orange one, 3 hydrogens. So I can assign this one to be priority 3. All right, but what about my other two? My lists are tied. So now we're just going to continue to move down the line here. So now I'm going to make my list for this carbon, which is 3 hydrogens. And for this carbon, which is a carbon and 2 hydrogens. So we just keep on moving down the line until we get a break in our tie. So that butyl group, that longer group, is going to be priority 2. And this one priority 1. And this one's priority 2. So now we're going to go 1 to 2, 2 to 3, and 3 back to 1. And I'm going in the counterclockwise direction. However, my hydrogen is not pointing into the page, but pointing out of the page. So I have to swap my rules for my R and my S. Now counterclockwise will be that R stereoisomer. Cool? All right, so we're going to pick up with this next class period and finish off chapter 5.